Let's start today by taking a step back and looking at the major components involved in web browsing when there's data stored persistently in a database somewhere. So you have the client, something like Firefox, you have the web server that's running on some machine somewhere, and the database server running on some machine somewhere. And usually those two servers are separate machines, possibly not even on the same network. They're just separated by the internet somewhere. In reality, though, it looks more like this, where you have multiple clients connecting to the web server at the same time. And I'm only showing two of them here, but realistically it'd be more like hundreds or thousands. But there's still only one web server and one database. So these two clients, or lots of different clients, are doing things at the same time. What does that mean when there's only one database? How does it handle the concurrency issues? So let's take a look at a little example in the context of the library web server. Let's say two patrons are connected at the same time. So the web server is going to have two threads or two processes running to handle each of those clients. And let's say they both try to check out the same book at the same time. And I don't just mean a book with the same title, I mean the actual same physical copy with the same serial number. So two threads running on the web server. They're both going to run some kind of insert command at the same time in order to insert a row into the checked out table saying some patron has checked out the book with serial number X. And that command is going to take some finite amount of time to run, and then it will finish. It's not instantaneous, though, so that's the important thing here. So what happens? You cannot have two of the same serial number in the checked out table because that's a primary key violation. So this is a race condition. So what happens in this case? Does the database just become corrupt? Does it somehow allow for two rows with the same primary key in the checked out table? Turns out the answer is no. Even without us doing anything specifically to prevent against this problem, the database management system automatically protects against this race. One of them will succeed and the other one will fail with a primary key violation. So if we go back here, either client A or B is successfully going to check out whatever the book is. And then the other thread or the other process, it will throw an exception and it'll just look like, oh, that book was already in the checked out table. And it's not magic or anything. The database management system is essentially protecting against this race without us having to do anything about it. And the way the DBMS protects against this race is through something called a transaction. By default, modification commands such as inserts and deletes and updates are done in a transaction. And basically what that means is they will either completely fail or completely succeed. So if it started working on the operation and got a little bit done and then something went wrong, any modifications it had made will be undone and it will appear as though nothing had ever happened in that transaction. Or if it gets to the end of the operation and everything worked, then it has 100% succeeded and everything is made permanent on the database. And importantly, this property is guaranteed even with concurrent transactions that could potentially result in a race or where they're both trying to modify the same table in a conflicting way. So in our example here, one of these insert commands will completely succeed and insert a row into the checked out table, and one of them will completely fail. And to the one that fails, it will just look like the primary key was already there before it even tried to insert it, and so it will just be a primary key violation. And which one succeeds and which one fails is essentially an arbitrary choice, and it's up to the DBMS to detect these conflicting transactions and make one of them succeed and make one of them fail. And this idea of transactions is part of a bigger design principle in relational database engines called ACID. This is just an acronym that stands for atomicity, consistency, isolation, and durability. And all four of these properties are very important in a relational database engine. Atomicity, we've already kind of seen, just means that operations either completely succeed or completely fail, and they will never partially run and leave the database in some corrupt state. Consistency means that operations will never result in violated integrity constraints, or in other words, there is no such thing as an SQL command that will let you break any integrity constraints, such as primary key constraints or foreign key constraints or cascade rules. And these first two combined, atomicity kind of helps to implement consistency, because if operations either completely succeed or completely fail, and the only possible operations are ones that would leave the database in a consistent state, then we know that the database will always be in a consistent state. Isolation at a basic level means that transactions will not interfere with each other, even if they are concurrent and would normally cause a race condition or some kind of conflict. It will appear as though they are running in isolation and nothing else is going on the system at that time. So in the example where two people were trying to check out the same book, to the transaction that failed, it just looked like that primary key was already in the checked out table the whole time. And to the one that succeeded, it just looked like it was not there and it was able to insert the primary key. And the system will automatically detect any such conflicts and resolve them and let one transaction succeed and have one of them completely fail. Or sometimes it's necessary for both of them to fail. There are different isolation levels, though, and we can turn down the isolation level and sort of start to violate this isolation rule. Durability means that the result of a completed operation will not be lost. And that seems pretty basic and intuitive, but consider in a programming language, if you're trying to write some bytes to a file, so you call some write method, even after that method completes, you are not guaranteed that those bytes are in the file. So if the power goes out or your program crashes right after the call to write, the file may not actually contain the information when you restart. And that's because the OS can decide to buffer the write in memory until some later time before actually committing it to the file. In a database, as soon as the server responds with a either completed or failed operation, if it's completed, you know that the information is permanent on the server. And the good news is that any modern relational database management system will provide these ACID properties, including MySQL and MariaDB, which is the open source variant that we are using. But we do still have to know how to use ACID, and we have to know what we're doing. It's not just automatically going to do the right thing for us. So let's look at another example. Let's say we have a bank account database where this accounts table is just holding account balances. And the operation we want to do is transfer some money from one account to another. So you could imagine doing this in two operations where we set the balance of account X to balance minus 100, and then we add 100 to the balance of account Y. So just take it out of one and add it to the other. And each of these two things are one individual operation, so each of them separately will either completely fail or completely succeed. So what happens if something goes wrong in between these two operations? So after subtracting the balance from one, say the server crashes. And even though we have ACID and we have each of these operations running in a transaction, this is what happens. The first operation will completely succeed and thus remove $100 from account X. The second operation will completely fail and thus never add $100 to the other account. So the customer has just lost $100. So what we need is something like this, where the whole thing is done as one operation that will either completely fail or completely succeed. So if it completely fails, then the subtracting of $100 will never happen unless the adding of $100 also happens, in which case it completely succeeds. So if the server crashes somewhere in between this, then once the server gets back up and running and restarts, anything that had happened or partially happened in this one operation will be undone. More precisely, it never happened in the first place. It was never committed in the first place. It was working on it in sort of a temporary space, and then it will never actually make the changes permanent. So the customer doesn't lose their money. They would have to do the transfer again, but that's better than having them lose money. So how do we make this happen? How do we do both of these commands as a single operation or as a single transaction? And SQL just provides a simple way of manually increasing the scope of a transaction. So we can use start transaction and commit to mark the beginning and end of a transaction. And then we can put any SQL commands we want in there, and they will be treated as one atomic operation. So if something goes wrong in between the start and the commit, then it's as if nothing ever happened at all. If the commit is never reached, then the changes are never made permanent. So even if a couple of the SQL commands completed, any progress they made will be completely undone, and the database will be left in a consistent state as though the transaction never happened. Alternatively, if we detect that something has gone wrong and we know that we don't want to complete the transaction or we can't complete the transaction, then we can roll back instead of commit. And that has the same effect as if the server automatically detects that something went wrong with the transaction. It will just undo any changes that it had made up to that point. In reality, it's not actually undoing anything. It's that no changes were ever really made because these operations are done in sort of a sandbox mode until the commit, at which point they're made permanent. So if we have to undo a transaction, then we just essentially throw away the sandbox and then everything's back to normal. So let's take a look at a little example. Let's say we have two SQL sessions running. So here's the first session, and we'll show the next one in a second. By default, a transaction is running in, like I said, sort of like a sandbox, where any changes made in that transaction are only visible within the transaction or within that session. So if I start a transaction over here in session 1, change some things, so maybe insert or delete some rows or whatever, if I then do a select, it will show me those added rows or those deleted rows. So it will select the new data that was changed within the transaction. But over here, if I have another session connected to the same SQL server, and I do a select on the same table that the other session is modifying, this other session is still going to see the old data. It will not see anything that the first transaction has done yet. Then, if the first session commits its transaction and then session 2 does a select again, then at that point it will see the new data since it's been committed. So think of a transaction as a temporary sandbox where the rest of the world can't see it until it's committed. That is, at least by default. We can change the isolation level and sort of change this behavior a little bit, but we'll see that later. Alternatively, if the transaction was rolled back and the second session does a select again, then it will still just see the old data, and it's as if nothing has ever happened. So let's play around with this in actual SQL terminals and see how this all works. So I have here two terminals already connected to a MySQL server. So two separate sessions, completely separate sessions, but connected to the same database server. And I'm in this database called transaction demo, so let's see what's in here. Just one table called A, and let's describe it. So A has just one column, X, which is an int and is the primary key. So we're just going to do some really simple demos to see how transactions work. Let's see what's in the table. Select star from A. So nothing in there right now. Okay, so in one of these sessions, let's start a transaction and then insert something into that table. So insert into A, values 5. Okay, now if I do select star from A, there's the 5. It shows up in this session. But remember, this is a transaction, which means it's kind of like a sandbox. So if I come over to my other session and I do select star from A, there's nothing in it. So this is not really a real file. It's not real data. It's not actually in the database. If I commit and select star from A, it still shows up here. Now if I select star from A in my other session, it is showing up. So it is now made permanent in the database. And the sandbox is gone since commit stopped the transaction, but it made the sandbox permanent on the database. Let's try another thing. Let's start a new transaction over here, and let's insert something else. Insert into A values 10. So select star from A, there's the 5 and the 10. Select star from A in the other session, the 10 is not there. And if I roll back my transaction, now if I select everything in this session, the 10 is gone. Select everything in this session, it was never there in the first place. Since, again, this was a transaction, and when I typed roll back up here, it essentially just threw away that transaction or threw away the sandbox and never made those changes permanent on the server. One more thing to clarify about rollback. So manually rolling back, like I just did, is usually not that useful because if a transaction fails, the system will automatically roll it back for you. You usually just want to try to commit your transaction, and either it works or it doesn't. And it will tell you whether it worked or not. Manually rolling back, though, can be useful when you're like I was just doing, when you're kind of just playing around in the database and you want to try some things without any risk of modifying the permanent server. So sometimes companies will give new employees the ability to mess with the database, but only inside of a transaction, and then they're not allowed to commit, they're only allowed to roll back. So it's a safe way to experiment and see what a query would do. If we do detect an error, though, like in software or while we're working on our commands, then we can manually roll back. Importantly, though, I wanted to point out that rollback will automatically happen if the system detects that it can no longer complete the transaction due to another transaction interfering or conflicting with it.